In this video, we're going to explore an important consequence of Newton's second law of motion. And to explore this concept, we're going to analyze the force required to stop the same car traveling with the same initial velocity in two different ways. So if this is the car with an initial velocity of 20 meters per second, and we want to stop this car, that is, the car will have a final velocity of 0 meters per second. If the car is initially traveling in this direction with this velocity, then you know by Newton's second law of motion you need to apply a force in the opposite direction that this car is moving, and that force is going to cause this car to accelerate in the opposite direction of motion. Remember, Newton's second law of motion tells us that forces cause objects to accelerate in the direction of the net external force. Now in this video, what I want to do is I want to analyze the force required to stop this car over this distance here, and the force required to stop the same car with the same initial velocity over this distance here. So what we'll see is that even though this car has initial velocity in this direction, we still are going to have to apply a force in the opposite direction that this car is moving, and this force is still going to cause this car to accelerate in that same direction. Now if I call this force 1 and I call this force 2, now what we're going to see in this video is that it's going to take more force to stop this car in a shorter distance than it will to stop that same car in a greater distance. So to emphasize that point, a greater force is going to be required to stop a car in a shorter distance than if you want to apply a smaller force over a larger distance. So in this case, this is going to be a relatively small force compared to this force right here. So what we're going to see is that the distance over which these forces act, and we'll call this delta x1, will be different than the distance over which this force has to act in order to cause the cars to come to a stop. And since the distances over which the forces act will be different, the rate at which the cars slow down will be different in both cases. And the rate at which the car slows down is really going to be the acceleration of the car, that is, the deceleration, how fast the car slows down. So let's figure out how much force is required to stop this car in this distance. And in this case, let's say that the distance over which this force acts is going to be 100 meters. And our question is, how much force is required to stop this car? So we're going to be looking for the force required to stop this car. And let's assume that this car has a mass of 1,000 kilograms. And so we're going to try to find the force required to stop this car. Now the thing that we don't know is we don't know what the acceleration of the car is. We do know the distance over which this car has to slow down, and in this case this is going to be a distance of 100 meters. We know both the initial and the final velocity of the car, and in this case the initial velocity is going to be 20 meters per second, and the final velocity is going to be 0 meters per second. The car is going to come to a stop. The thing that we don't know is how fast this car comes to a stop, so we can't calculate the acceleration of the car based on the definition of acceleration. But we do know a relationship between the final velocity of the car squared and the initial velocity of the car and the acceleration and the change in distance, and that is the final velocity squared equals the initial velocity squared plus 2 times the acceleration over the distance in which this car is going to slow down. Now in this case we know the final velocity of the car is 0, so we can rewrite this as 0 equals the initial velocity of the car squared plus 2 times the acceleration of the car times the distance over which this car is going to slow down. And what we're looking for is we're looking for the acceleration, because once we know the acceleration of the car, we can use Newton's second law to figure out how much force is required to stop the car. So what we need to do is we need to subtract the initial velocity squared from both sides. What you do to one side of an equation, you do to the other. And when you do that, you get minus v initial squared equals 2 times the acceleration times the distance over which this car is going to come to a stop. And since we're looking for the acceleration of the car, we're going to divide both sides by 2 times the distance over which this car slows down. So what you do to one side of an equation, you do to the other. And what you should notice is that this 2 cancels out with this 2, and this delta x cancels out with this delta x. And then you get an expression for the acceleration of the car equals minus the initial velocity squared divided by 2 times the distance over which this car is going to slow down. So this is going to be our expression for the acceleration of the car. Now to figure out the acceleration of the car that's slowing down over a distance of 100 meters, we're going to just plug in the information that we know, minus v initial squared divided by 2 times the distance over which it slows down. This is going to equal, we said that the initial velocity of this car was a positive 20 meters per second, and then we're going to square the entire term, and then we're going to divide this by 2 times the distance over which this car is going to slow down, which in this case is 100 meters. And when we do this out, you should get minus 400 meters squared per second squared divided by 2 times 100 meters, which would be 200 meters. And when you divide negative 400 meters squared per second squared by 200, you should get minus 2 meters per second squared. And that's going to be the acceleration of this car over that 100-meter distance. Now to figure out the force required to stop this car, we're just going to apply Newton's second law, which says that if you add up the forces acting on the car, it's going to equal the mass of the car times the acceleration of the car. And don't forget, Newton's second law is a vector equation indicating that it has both magnitude and direction. And in this case, we said that the car had a mass of 1,000 kilograms. And in this case, we're going to slow this down at a rate of -2 meters per second squared. And so the force required to stop this car, initially traveling at 20 meters per second over a distance of 100 meters, is going to be minus 2,000 newtons. And notice the negative sign indicating the direction in which this force has to act. It's going to act in the opposite direction that this car is moving. Now what we're going to do is we're going to figure out how much force is required to stop that same car in a shorter distance. And in this case, we're going to assume that the distance over which we're going to stop this car is going to be 50 meters. So we're going to go about this problem much in the same way that we did the previous problem. We don't know what the acceleration of the car is, so that's going to be our question mark, but we do know the initial velocity of the car is 20 meters per second. We know the final velocity of the car is 0 meters per second, and we know the distance over which this car is going to come to a stop, which in this case is going to work out to be 50 meters. We're going to use the same equation that we used in the last example, which was the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the distance over which the car has to come to a stop. Now, instead of going through all the algebra, we know that the acceleration of the car is going to equal minus the initial velocity of the car squared divided by 2 times the distance over which that car has to come to a stop. Now in this case, this works out to be minus 20 meters per second. The initial velocity of the car remains the same, and we have to square it. And then we're going to divide that by 2 times the distance over which this car comes to a stop, which in this case was half the distance, or 50 meters. So this will work out to be minus 400 meters squared per second squared divided by 2 times 50 will work out to be 100 meters. And when you divide negative 400 meters squared per second squared by 100 meters, you get minus 4 meters per second squared. And that's going to be how fast the car has to slow down in a shorter distance. Notice the acceleration is greater because the car is going to have to come to a stop in a much shorter distance. Now to figure out the force required to stop this car, we're going to use Newton's second law again, which says that if you add up the forces acting on the car, it's going to equal the mass of the car times the acceleration of the car. And don't forget that this is a vector equation because the force and the acceleration both have magnitude and direction. And so this is going to equal 1,000 kilograms, which again is the mass of the car. And now in this case, we're going to slow this car down at 4 meters per second squared, which is twice the rate that we tried to slow the car down over a distance of 100 meters. And in this case, 1,000 kilograms times negative 4 meters per second squared will be 4,000 newtons. So a force of 4,000 newtons has to act on the car when you want to stop it in a shorter distance. And again, notice the direction in which the force has to act. The force has to act in the negative direction, in the opposite direction that this car is initially moving. So let's summarize a few key points that I brought up in this video. So the first point is, the force required to stop the car depends on the distance that you want to stop the car in. The shorter the distance you want to stop the car in, the more force required to stop the car. And the second point is, the faster you want to stop a car, that is, the greater the car's acceleration, the more force that you'll have to apply to stop the car.